In section 4.1, we're going to talk about functions and finding their maximums and minimum value. The first definition we have is about the absolute maximum and minimum. Let f be defined on an interval containing some point c. Then f has an absolute maximum if its height, f of c, is greater than or equal to f of x for every x in the interval I. Similarly, if f has an absolute minimum on I, that means that the height at every point is lower than the next height for every x in I. So let's take a look at some examples. Sometimes it's easier to see. Let's look at this first parabola. It has an absolute minimum of 0, but no maximum. Here's our minimum at 0. But it has no absolute maximum because the function takes off to infinity as x gets bigger and bigger. On our next picture, we're not taking the entire parabola, we're just taking a closed interval from 0 to 2. Because we're including those endpoints, we have an absolute minimum height. So the lowest the graph goes is a height of 0 at 0. And the highest the graph goes at this point is 4 at the number 2. Now, if we look at this interval that's half open, so we're undefined here at 0, we're not including that point. We're just getting incredibly close. Because the function's not defined for this point, we have no absolute minimum. The maximum is the closed endpoint, so that still occurs at 4. Now, if it's an entirely open interval, then we have no maximum or minimum. A little bit confusing, but basically if the endpoint's included, then it can be a maximum or a minimum. Here's some other examples. On a split function, if in this particular case, we actually have 2 places where we hit our minimum value. So the answer to the absolute minimum value is 0, but that happens at x equals 0 and at x equals 1. There's no maximum because a line just takes off to infinity, so it's just going to get bigger and bigger and bigger. Now, on this function, we have an absolute minimum on the second function here at a, right, because that's the lowest height that we have. Now, it looks like our biggest height is here, but you notice that's an open circle, so the function's actually not including that particular point, so we have no absolute maximum value. First theorem for this section is called the extreme value theorem, and it says that a function that is continuous on the closed interval from a to b has an absolute maximum and an absolute minimum value on that interval. So a couple of things to note there. The maximum or minimum might be at the endpoints A or B, right? Or it might happen somewhere in the middle. Let's take a look at a picture of that. On our first diagram, we have a closed interval because we're including the endpoints. So we have an absolute maximum at A, that's the highest the graph ever reaches on the y-axis, and we have a minimum at C because that's the lowest the graph ever reaches. Even though we're defined at B, we don't have a maximum or a minimum value there. Okay, now what's our next function? We're split. The last time we looked at a split function, it was not including the highest point, but here our closed dot is at C, right, the highest point that we can come to. So we have an absolute maximum at C, but no minimum value on this picture. This is kind of extreme, but it shows all of our different situations. So we're just going to walk through these in alphabetic order here. So at A, our left endpoint, there's no absolute minimum, no smaller value on the entire function. That's our lowest point or our smallest height. At C, we get a local maximum. Now, local just means that there's nothing nearby that's bigger or smaller than that value. Absolute is the biggest, so I'm going to actually jump over here. We're going to come out of order. We're going to jump over here to E. That is the highest point on the graph, and so it's an absolute. It's also a local, though, because it's inside that window from A to B. So it's both local and absolute. That gets a little bit tricky. We have a local minimum at D, because near this function, we're coming down and we're coming down, so that's the lowest point in that section. And that kind of gives you an example of each style as you're going through there. Okay. Now, as far as local versus absolute, our local maximum and minimum values. Suppose I is some interval where f is defined and c is some interior point on that interval. If f of c is greater than or equal to f of x for all x in some open interval containing c, then f of c is a local maximum value. Just the opposite is true for the minimum. So that might have sounded a little bit abstract. What does that actually mean? Okay, so C is an interior point. So if we have a segment of the graph from A to B, then C is some point inside. Doesn't matter where it's at. It could be here, it could be here. We just have some point C in between A and B. So now if we evaluate the function at f of c, it's just saying that that's the largest point, then it's a maximum. Call that one C1 and we'll call this one C2. If there's some other point on the graph, it just means that it's the smallest point. Well, it's hard to see with my pen here. But if it's the smallest point on the graph, then it is a minimum. Okay. If you have a local maximum at some point, remember what the definition of our first derivative is? It gives the slope of the tangent line. So if it's a maximum, its tangent has a slope of 0, and it comes right across the top here. All right, our next theorem is the local extreme point theorem. Just says that if f has a local maximum or minimum value at c, and the derivative exists at that point, then the derivative is equal to 0. So if you come back to that picture again, it's defined at that point, the derivative is 0 at that point, and sure enough, we've got a maximum. In some cases, a minimum. All right, our next definition we talk about that we're going to use over and over and over is our critical point. An interior point of the domain of f at which the derivative equals 0 or the derivative fails to exist is called a critical point. Cases where the derivative fails to exist is going to occur, maybe if we cause division by 0, for example. Okay. So in this case, in the first figure here, our local minimum exists. We do have a local minimum, even though it's not defined on the function. And then here we have a cusp coming up, so a sharp point. So the derivative doesn't exist, but we still have a maximum at that point. Okay. Some other kind of strange cases. Here's one where the derivative is equal to 0, right, because our tangent line is horizontal, but it doesn't actually create a maximum or a minimum. So that theorem doesn't go both ways. This later we'll talk about when we talk about concavity. This is an inflection point. Most importantly, it did have a critical value there, but it did not create a maximum or a minimum. We'll look at how to prove that in a minute. If the derivative does not exist, here we have a vertical tangent line, and remember the slope of a vertical line is undefined. So that's why the derivative doesn't exist, and we have no local max or min. But we still might get a change or a critical number when we went to evaluate.